so in our previous segment, we talked about how rocks can be dated relatively. So that means that this rock layer is older than this rock layer. Now we want to put actual numbers. How much older is it? And so we're going to use radioactivity in order to do this. So radioactivity comes from the nucleus of the atom. So we said that an atom consisted of a nucleus, and then it's got electrons that are in orbit around it. Inside the nucleus are going to be protons and neutrons. So depending on the number of protons and neutrons in there, we could have a radioactive nucleus. Okay, so certain nucleuses are more radioactive than others. So let's pretend that we go out and we just grab some hydrogen out of the air. So hydrogen is going to be given by the letter H, and ordinary hydrogen, so about 99% of the time, the hydrogen that you grab is only going to have one proton in it. That's it. And then it's got an electron in orbit around it. Now, rarer than ordinary hydrogen is a different kind of hydrogen called deuterium. So it's still given the letter H, but it's going to have one proton and it's going to have one neutron in its nucleus. And even rarer still is going to be a type of hydrogen called tritium that is going to have one proton and it's going to have two neutrons. So notice that no matter what it is, it's got one proton. Every hydrogen has to have one proton. So that's the atomic number. That's the number on the periodic table that doesn't have the decimal point. But they have different numbers of neutrons, so these are different kinds of isotopes of hydrogen. And you can have isotopes of helium, isotopes of lithium. So every element in the periodic table is going to have different isotopes. So how do we write the symbol for a particular isotope? So first, we write down here the number of protons. 1, 1, and 1. Okay, next we write down the number of protons plus the number of neutrons. So 1 plus 0 is 1. 1 plus 1 is 2. And then 1 plus 2 is 3. So I'd like to be able to read, if I give you the isotope, you should be able to tell me how many protons, how many neutrons does it have. Or if I tell you how many protons and neutrons it has, you should be able to write one of these things that goes with it. Okay, now let's talk about radioactivity. So some nuclei have too much energy because they might have too many protons or they might have too many neutrons. And so what will happen is that it will spontaneously fall apart. We're going to call this nuclear fission when this happens. And we will be able to predict how much of it's going to be left by using the concept of a half-life. So let's talk about the radioactive particles that are given off whenever something breaks apart through nuclear fission. So one particle that can be given off is going to be called the alpha particle. So that's the Greek letter A for alpha. And it's going to have two protons and it's going to have atomic mass of 4. So 2 protons, 2 neutrons, 2 plus 2 is 4. So we're going to say it's got 2 and a 4. Now that is helium. So ordinary helium in its nucleus has 2 protons and 2 neutrons, so 2 plus 2 is 4. So a helium nucleus is an alpha particle. So in some radioactive decays, it will give off a helium nucleus. Another thing it can give off is a beta particle. So that's this thing. So that's the Greek letter B for beta. And it is an ordinary electron. Now there's another kind of a beta particle called the beta plus, which is an electron, but it's got a positive charge, so let's not worry about that. The third kind of particle that could be given off is a photon of light. And so we're going to give it the symbol G for gamma. And so we're going to say that this is electromagnetic radiation. So you might be familiar with radio waves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. Well, this one is gamma, G for gamma, radiation. It's the most powerful radiation. It has the most energy. So this is another type of particle given off in a radioactive decay. So here's a picture that shows what happens when you start with uranium, a radioactive piece of uranium, and it breaks apart, it goes through nuclear fission, and it gives off all of these different kinds of particles. All I want you to see from this picture is one radioactive substance can end up turning into a whole bunch of other radioactive substances. This is the reason why nuclear fission gives off a lot of radioactive materials that can be very dangerous. So this is a radioactive decay series beginning with uranium and then ending up with lead down there at the bottom. Now each of those decays, so starting with uranium and then turning into something, which turns into something, which turns into something, takes a certain amount of time for that to happen. And that time is going to be related to the half-life of it. So here is a formula for how to calculate the amount of time that it's going to take for a particular amount of substance that you begin with to turn into something else. So T in that formula is going to be the amount of time it takes. Okay, but then you notice there's another T. So that T, T1/2, is the half-life. Every radioactive substance has its own unique half-life number that goes with it. Sometimes it's in billions of years. Other times it's in seconds. So if we look at this chart here, here's different kinds of radioactive substances, and then next to it is their half-lives. So the half-life is the time it's going to take for half of it to decay. So let's go back to here, and let's pretend that we start off with 100% of something. Then at the end of one half-life, only 50% of that original material will be there. So that means that you will have 50% of it will have turned into some other radioactive substance. Okay, at the end of two half-lives, you're now down to 25%. 1/2 of 50% is 25%. So that means now the grand total of other stuff is 75%. So here's the original material, 100%, 50%, 25%. So let's also put down the amount of time that has elapsed. So let's just make up a number. Let's say the half-life was 10 years. So we click our stopwatch right there. So 0 time has gone by before we click our stopwatch. Now we click it. At the end of 10 years, now you're left with 50%. At the end of another 10 years, so 10 plus 10 is 20, so 20 years have elapsed, Now you're down to 25%. At the end of 30 years, how much would be left? One half of 25%, which is 12.5%. And then what would be this number here? Okay, 100 minus 12.5 is going to be 87.5%. And we could keep going, but I'm not going to. So if we wanted to know exactly how much time elapses, we could use that formula, but we're not going to. So what we're going to be using and what you need to be able to read on the exam is going to be a graph. So a graph, and this is going to be the amount of material that's left over. So we start at 100, and then after one half-life we're down to 50, and then at the end of another half-life we're down to 25, and then this is the number of half-lives. So one half-life we're down to 50%. Two half-lives, so two half-lives, we're down to here. So if we were to connect these lines, then we would get something like that. So you should be able to read a graph and then determine, depending on the number of half-lives that have gone by, how much of it is left over. Now there's another way of writing this which you should be familiar for the exam. So instead of saying 50%, 50%, we could say it's a 1-to-1 ratio. Okay, what would this one be? Okay, how many times does 25 go into 75? So this would be a 1-to-3 ratio. How many times does this go into this? Well, you're going to need a calculator, but about 7. So this would be a 1-to-7 ratio. So just be aware, you might see it written that way on the exam instead of percentages. So here is a typical question that you should be able to answer on the exam. And the best way to do this is to make a table. So in the first column of the table is your time. How much time has elapsed? And then in the second column, write down how much is left. And by making a table like that, you can figure out these kinds of math problems. All right, let's take a break. When we come back, let's apply this to rocks.